All right, so we dealt with the situation where we just have, some point particle, but now we're going to deal with many, many particles. And there's two basic worlds in which we were describing many, many particles. One was fluids, and one was statistical physics. And the big difference here is with fluids, even though it is the collective motion of many particles, we actually ignored that there were particles there, and we just talked about the bulk properties, things like pressure, whereas with statistical physics, we actually talked about, the thermal kinetic energy of a particular particle. We actually looked at the different particles. Einstein, through pollen grains being bombarded by water molecules, told us that fluids are actually made of molecules. So over here, we have our molecular description, and then this is just, bulk properties, right? Just properties of the fluid as a whole, pressure, Reynolds number, things like that. So in the rest of this video, just this one, I'm gonna talk about fluid statics, because with fluids we had fluid statics where the liquid isn't moving, and then fluid dynamics. So the first thing we learned in fluid statics was the pressure here. And so the thing that I would keep in mind when you're trying to think about just pressure as a concept is this example where you have some window here that has an area A, and there's some pressure. Let's say this is like the window inside a spaceship. It's out in space, and there's some small pressure outside, right? So there's some big pressure inside, like this is big, pressure outside is small. And so there's a force that's going to be caused by this difference in pressure. And since we have a higher pressure inside, low pressure outside, the force is going to be this direction. So we will have a force acting on the window. And so if I asked you, how big is that force? The magnitude of that force is going to be equal to P in minus P out. Since we know P out is smaller, we know this is going to be a positive number, and then just times the area of that window. And so that's sort of like the picture to have in mind when you're thinking about pressure. So we started by thinking about incompressible fluids, things like water. And so we have this equation that describes what the increase in pressure is if you move up or down in some incompressible fluid, right? So the picture to have in mind here is you have some fluid here, right? It's like a pool, swimming pool or something. And, up here we have, like, let's say 1 atmosphere. This is just the air. And so let's say you're right here, and you want to know what's the pressure at the bottom of the pool, and the height of the pool is a height h. And so you travel right here, and let's say there's no meniscus or anything. You are still at 1 atmosphere right here, right below the surface. And then we move down in the fluid. And then what's the pressure down here at the bottom? Well, the pressure at the bottom is going to be equal to 1 atmosphere plus rho of water, g, and then times this h, the distance that you moved down in the fluid from that top surface. Then we started talking about, oh, you know what, let me actually give you a second example of this, because this is actually a really interesting one, and I also think a pretty instructive one. So the actual way you can actually measure pressure is if you have a container like this, and we have some fluid in this container, right? Some fluid like here. And then we also have a test tube that's as high as we want, like a really high test tube coming out of here. And then let's say we suck the air out. So, we say that, right here we say the pressure is equal to 0. So we suck the air out so that the water level that would have been here actually goes upward, and we have the water go up. It basically gets sucked up because we took the pressure to be 0. We sucked all the air out of that test tube, so the water went up into it. And so even though you sucked out all the air, the water doesn't actually go all the way up, right? So it doesn't go all the way to the top of the test tube. And so why is that? And why is this so interesting? So the reason why that is is because let's say we're on, we're trying to figure out what is the pressure. You're like, the thing you're trying to figure out is like, what is pressure here, right? The pressure just like right near the surface. Well, you can actually figure out that the pressure right here at the surface, right, that's the same as the pressure right below the surface, and that's the same as the pressure at any point in this same horizontal line wherever you go, right? So including right here at this point. And so if we know the pressure is 0 here, right, the pressure is 0 down here or anywhere up in this tube, and then we start moving down in this fluid like that, we know we're trying to figure out what the pressure is down here. And so if the pressure is 0, up here at the top of the tube, right, the pressure is 0 right there, then we know that going down to this point here, we're going to have the pressure equal to 0 where we started up at the top of the, right where the surface is in the tube, and then plus rho of this water, G, and then H, right? So this is our H for this particular example. And so the reason why this is so cool is because just based on the height of, based on this H here, we can figure out the pressure right here at this point, right? Right here at this point, which is the same as the pressure right here, which is the same as pressure right here, same as the pressure right there. And so just by knowing H, right, the pressure now is rho water GH, just by knowing that height that the water was sucked up into this tube, we can actually figure out the pressure that's in the atmosphere over here. So if we're on Earth, we're going to get this is equal to, this whole thing is going to be equal to 1 atmosphere, which is kind of cool. And, if you're on Earth, this is going to be, and we have water, so this is going to be 10 meters for water. Or if you have something like, mercury, then since our rho, we're not going to have rho of water, right? So this is going to be, right, so this rho could be rho of mercury instead. And so instead of going 10 meters up, instead of, the height over here in this test tube being 10 meters, this were mercury in the whole container here, right? If this container instead had mercury in it, so like something like this is mercury, then I'm putting in this container, then what you would get actually is the mercury would rise only 760 millimeters. And that's why 760 millimeters is equal to 1 atmosphere, because this is how they measure in millimeters of mercury. So that's just a cool example. I think that's really instructive, so that's why I put it in here. Then another equation that I think most of you are familiar with, so I won't go through it in detail, but this is basically the ideal gas law, which relates the number of particles, the temperature, Boltzmann's constant, and pressure and volume. And the example you can keep in mind here is if you have, say, some balloon or something with particles in it, and let's say you keep it at some, you don't let the temperature change, but then you do shrink it down. Let's say we shrink this down. We're going to shrink it down to a smaller balloon with the same number of particles, and we've shrunk it down now. And let's say if we keep to the temperature is fixed, then basically we can figure out, since the number of particles is the same, Boltzmann's constant is the same, and we've changed the volume now, we're going to be able to figure out how much the pressure changes from making that balloon smaller. One other equation, and this is now, so now we're dealing with compressible fluids, right? So this was an equation we used for the pressure of basically in the atmosphere. So what you should basically keep in mind is you have a bunch of you have particles of air. This is like the atmosphere of Earth, right? So this is like Earth, and basically what this equation does is it helps you. It basically describes what the pressure will be if you're going, say, from 1 atmosphere, and then you want to figure out what the pressure is say, higher up here at some height, some height h. So now buoyancy. So buoyancy is just a force on any object that's in fluid, right? So it's like we have some container, and then there's, say, some fluid in it. Let's put a balloon in there. And so this balloon will have some force. Let's make it a force. Black. So we have some force up like this. So this is the buoyant force on that, and the buoyant force. And keep in mind that it's the pressure that the density that we care about is the density of the fluid that it's in times the volume of the object. So it's, can be confusing. Am I using the density of the object? No, you're using the density of the fluid that it's in times the volume of the object times gravity. And so this can also be thought of as, you can just write this as basically the weight of fluid displaced. And it's helpful to think of it like that, because if you had this same balloon, so you take this same balloon and you put it in a different fluid, like, let's say this is helium, if it's in water, right? So if it's in water, it'll have some force up like this, some big force up like this, because it's displacing water. But if instead you now bring the balloon over here in the air, then it'll still have a buoyant force. That balloon will still have a buoyant force up, but it'll be a smaller F buoyant for air, because it's displacing something that has a lower density. Air has lower density than water. So surface tension, this one I got a lot of questions on, and so let's go back to the example that the demo we did in class to learn this. So basically, what we had was we had some surface here, and then there was some bubble. There was a bubble right here, and then we stuck a bar at one edge of this, like that, and then there was no bubble over here. And what we noticed was that this bar had a force that pulled it that way, right? And so what's going on here is actually you have two surfaces. So the bubble is actually, two surfaces here. So let me try to draw this for you. Right. So basically, you have a fluid surface on the top, and this fluid surface on the top. So okay, let me first draw the length of this thing, which is L. And so the top surface is going to have a force just from, along right here. So this length here is basically the place where the top surface of this, right? So this is like, basically in here, like in all of here, there's water. And then there's basically an interface with water to air up here at the top, and there's also an interface down here at the bottom. And so the top surface, the force that we're going to get is going to be equal to gamma, and that gamma is basically O gamma specifically for this interface of water to air. So let's just call it gamma water. And then times that length L. And then also on the bottom here, we're going to have another force, right? So basically, it's on the, I'm going to draw it as a dotted line because it's sort of on the bottom surface of the bar. And that's going to also be pulling, it's going to be pulling this way. And that F is also equal to the same gamma water L. And so we add those up, so we have 2 gamma water L that is pulling it. So that's basically what's going on is going on here. And then that basically led us to the situation where we were talking about bubbles, right? So if we have a bubble now, or let's say rather, we have a situation where you have some container, we have a lot of containers. Basically you have a container that has some fluid in it, and then there's air, there's basically a cavity of air. You could call it a bubble, but it's a cavity, so there's only one interface, one water-air interface right here. And this equation is basically describing the difference between P in and P out. And so if you know the radius of this bubble, so this is the radius here, we know the radius is r, and we know that the interface has a gamma of, let's just call that interface gamma. Then we know that the change in pressure inside to outside is 2 gamma over r. So that's one example where you'd see this. Another example is if you just have, so a lot of people asked about this, if you just have a bubble that's made of, it's basically a soapy bubble that's floating in air. So right, so if we have like air in here, and then we have like soapy water, right? So there's water in there, and then we have air outside. So I'm just gonna make this blue so we know that this is water in here. All right, let's do this. This is our watercolor. So we have water in here. And so one thing that people asked a lot is going from air to water back to air, right? So we have two surfaces here. What's the change in pressure for P in, P out here, right? So P in minus P out in this situation, because we have two water-air interfaces, is actually going to be 4 gamma over r, where r is this distance here. And then, okay, one other really important example when it comes to curved surfaces is when we have a meniscus. So the situation you'd want to think about here is basically if you have, so let's do like we have like something like this, where this is water down here. And actually, let me do something just to challenge us. Let's actually have some. Let's put a surface here too, and let's make this one something like alcohol, and this one water. Now, what would the pressure be if I asked you, like, what is the pressure down here? Okay, like what is P equal to, question mark, down here, if we know that we have 1 atmosphere up here? So how would you find that pressure? So the way that you'd want to do it is you'd say, okay, we have 1 atmosphere, and so this is still air, so 1 atmosphere, and then right when we get to below the surface of the alcohol, like right anywhere around here, right above or right below the, actually no, right above the surface we have 1 atmosphere, but right below the surface, okay, we need to be really careful. So I'm just going to start, and so one thing whenever you're dealing with this is the trick to use to find the pressure somewhere you don't know is basically what you want is you want to find a line. So I'm going to use a dotted line. So you want to find this, and I'll use this magical color. So you want to find a dotted line basically to a place where you know the pressure, and then follow that line from the place where you know the pressure, like up here you know the pressure, and then follow it down, and then make sure that you're taking into account every place the pressure changes. So what I mean is that we know we have 1 atmosphere up here at the top, right? And so we follow it down to the top of this alcohol surface, and it's still 1 atmosphere, so we still have 1 atmosphere at the top of that alcohol surface, but then we go and we now have hit this meniscus, which is basically a bubble, and so what we're going to have is we're going to have a pressure drop because we're going from the inside of the bubble to the outside of the bubble of 2 gamma alcohol over the radius of this bubble, right, of the radius of this bubble. And then we're going to keep moving down in this. So we'll move down, and let's call this like H1. That's the height of the alcohol from the air through the alcohol to the water. We'll call that H1. So then we're going to go plus rho alcohol GH1. So that's an increase in pressure down. So now we've gotten to basically right above the water. And then we pass from the alcohol into the water. There's another bubble there, so we have to go minus 2 gamma, and this is the gamma going from the alcohol to the water, and we would give that to you if you if you had a problem like this. So I'm just doing a crazy thing like this just so I really challenge us and give us something to work with. So this is a gamma for alcohol to water. That's what this whole thing is. So this is just gamma here. Let me rewrite that in green. This is our gamma, and then divided by this is r, and that's actually let's do this r in green, okay? Because that's the r of this surface here, which is likely the same as our other r. And then we now need to move from here down this distance, and let's call this distance h2, and so then we have plus rho water GH2. Okay, so if we wanted to know that what the pressure is down here at the bottom, like this thing that we were looking for, that pressure is 1 atmosphere minus the pressure drop going through the first bubble, plus the increase in pressure moving down in the alcohol, minus the pressure drop going through the second bubble, and then plus the pressure increase going down through the water. So that is the statics fluid, and I know that was a lot, but I think that should be really helpful as just a review of all the things we covered for that.